Hi, I'm Amy Sullivan, and I'm the chair of the AAAR Endowment Committee, and it's my pleasure to welcome you to the 14th in our monthly series of ASNT lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So with these lectures, we hope to be able to highlight the amazing research happening in our community, give us an opportunity to all come together outside the annual conference, and also to tie our journal ASNT to other activities. So each month, the editors of ASNT select a high impact paper to be presented by its author. These lectures are being recorded and will be posted later to our YouTube channel, which you can access from the AAAR website under the events tab. In addition, each of these lectures are being hosted by one of AAAR's student chapters. So I want to thank everyone who's made these lectures possible, and also for all of you for joining us. And with that, I'll turn it over to AAAR's newest student chapter from the University of Miami. Thanks.
Thanks, Dr. Sullivan. Hello, everyone. Thank you for finding the time to join us today. I'm Shruti Chaudhary, PhD student at the Aerosol and Air Quality Research Laboratory. On behalf of University of Miami AAAR student chapter, I welcome you all to the lecture. The speaker for today's AAAR lecture series is Dr. Andy May. He's the Associate Professor at the Department of Civil, Environmental, and Geodetic Engineering at The Ohio State University. Today, he will talk about how size and composition of particles affect the performance of the Plantower sensors. We will have about 15 to 20 minutes at the end for question and answer session. Please feel free to submit your questions through chat during the seminar, and we will go through the questions in order. With that, I turn this over to Dr. Andy. The floor is yours.
Great, thank you. Thanks, Amy, for the introduction, and Shruti for introducing me. And I'll be talking about this paper, laboratory evaluation of the effects of particle size and composition on the performance of integrated devices containing Plantower particle sensors. And so we're going to loosely follow the paper in ESNT from 2021. Sort of going to add lib on top of the paper itself, just to, I don't know, make it a little more interesting for me. Hopefully it's interesting for you as well. I'd like to start with acknowledgements, because instead of rushing through this at the end, start with that. So our funder was ASHRAE for this project, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. My collaborators were co-PI Jordan Clark, and then Yang Yang was a PhD student who did a lot of the work that you'll be seeing today, and then Matt Young was a master's student who helped early on getting some of these things set up. And the way that ASHRAE works is that there's a project monitoring subcommittee for each project. So in a sense, it's kind of like an advisory board that gives feedback as we progress through the project. And so that was chaired by Dr. Brent Stevens, and BJ, Paolo, Li Ping, and Glenn all contributed to that as well. And then lastly, ASHRAE has a commercialism policy, and they typically don't like seeing trade names in presentations and things like that. Through some back and forth, we got them to agree for us to say that the use of these commercial names does not imply ASHRAE endorsement, approval, or certification. So I just want to make sure to state that up front. And so starting off, just what are low-cost sensors? I think most of us probably have some sort of definition of what these are in our head. And the way that I generally think about these is that it's something like less than $50 for a bare sensor. And so that's what we're seeing on the left here, one of the Plantower sensors, or less than about $300 for an integrated device. And so these Plantower sensors are integrated into Purple Air devices, which I'm sure, again, many of us are familiar with. And I realize that there are some exceptions to this, like the AlphaSense optical particle counter could be considered low cost, and it's more than $50 for a bare sensor. There's some integrated devices that are more than $300, but they also have things like gas sensors in them as well. But this is sort of generally how I like to think about these. And so why low-cost particle sensors? Really, over the past decade or so, the market for this technology rapidly grew. And so Initially, when these technologies came to market, they had things like infrared light sources, and they relied on thermal buoyancy to get the particles through the sensor. Over time, these evolved to a red light source, so going from about 950 nanometers to about 650 nanometers for the light source for some better particle detection. And they also added fans to these sensors to drive the airflow, so we're not relying on that thermal buoyancy. And really what ASHRAE was interested in is understanding how these sensors might be applicable for indoor air quality and smart building applications. And so sort of thinking more broadly, the COVID-19 pandemic led to a broader population of people thinking about indoor air quality. And so, many people from the AAAR community sort of spearheaded some of this messaging, and rather than name a few people and leave the rest out, I'm just going to keep it vague. If you're on the call, you know who you are. But really, the low-cost sensors make these measurements more accessible for sort of the everyday person. But really, the main question that I sort of think about when I think about these sensors is, are they reliable? And so that's really what we were trying to answer as part of this project. And so generally, these sensors respond to particle source events. And so what I'm showing here is a figure from a paper from Brett Singer and Woody Delp at Lawrence Berkeley National Lab, where they were testing a bunch of different sensors to some common indoor sources of particles. So shaking a dust mop or lighting candles, or these two sort of cooking related activities. And they're comparing the sensor to a Grimm optical particle counter. So that's the dark, or the thicker gray dashed line that we see in the figure. And so for most of these sources, we see the gray dashed line go up. We also see the other lines increase as well, suggesting that the particle, or that the low cost sensors are also responding to these particle sources. And so we saw that as well in our paper in Science and Technology for the Built Environment, where we tested different sensors, and these are anonymized because this is before we worked out that commercialism policy issue. But we're comparing our sensors to a combination of SMPS and APS as our reference. And for these 4 different particle source types, again, we're seeing that when our reference, the dark black line is increasing, we generally see these increases in the response from the sensors. And so what I've kind of glossed over in those past 2 figures is that the accuracy of the sensor should be questioned. And so here's just another example from another paper from Dong-Yang Rim's group at Penn State, looking at the number concentration reported by reference device to low-cost sensor number concentration. And so I've highlighted here this 1-to-1 line. So if on the data fall on the 1-to-1 line, we have sort of this perfect sensor that agrees exactly with our reference measurement. But as we see for these particle types of dust mites and pollen and cat fur, there's sort of this variable agreement with the reference. So in this case of cat fur, where we're sort of, the slope of this line might be around 1, but it's obviously much lower than that 1-to-1 line, suggesting that the low cost sensor is missing some of those particles. And sort of what does that mean? Sort of the quick take on detect particles is that if we have sort of a binary application, so thinking about like activating an exhaust fan over a stove, that accuracy may not matter as much. If we're just essentially using the sensor as kind of this on-off switch for localized particle control technology, maybe the inaccuracies don't matter as much. But if we're thinking about something like exposure assessment or continuous ventilation control, there may be some problems. So if our sensors are inaccurate, we're obviously going to have some inaccuracies in our exposure assessment. And if we're using these to control ventilation for an entire building, we may be running our fans when we don't need to, or not running our fans when we do need to. And so really what I'm talking about today is how size and composition really affect these accuracies. And so this figure taken from Yang Wang's paper in ASNT is looking at the role of particle size and how sensors respond. And so on the x-axis, we have the reference mass concentration from an SMPS. The y-axis is the low pulse occupancy, which is how this Shinye PPD sensor outputs its signal. And we're looking at 300, 600, and 900 nanometer PSL spheres. For the 300 nanometer spheres, the response is relatively linear over this entire range of particle concentrations. But we can contrast that with the 900 nanometer PSL spheres, where we have this sort of steeper slope where in this linear region before it eventually asymptotes out after we hit about 100 micrograms per cubic meter. So after we reach this concentration, the sensor is not continuing to increase in its output, even as the reference concentration increases. And so sort of a related problem to this is that many sensors report mass in different size fractions. And so here's work from Misty Levy-Zamora looking at one of the sensors that outputs PM10, PM2.5, and PM1. And that's compared to a reference measurement from a PDR monitor. And so the solid black lines are the PDR reference concentration. So if our sensor is perfect, these black lines would sit at the top of these gray regions. And so if we look at this example down here for cooking, the black line agrees reasonably well with that gray region. So relatively good agreement between what the sensor is claiming is PM2.5 and what the reference measure is saying. However, if we look at some of these other ones, like the talcum powder, the true mass concentration for talcum powder is way above what the sensors actually how the sensors actually responded. We have this maximum PM2.5 concentration from the sensor that's maybe around 20 micrograms per cubic meter, but the maximum in the reference instrument was approaching 200 micrograms per cubic meter. And so that's a case where the sensor is missing mass. But if we compare that to this residential figure down here in the bottom right, we see the black line agrees pretty well with the red region, which is PM1. So in this case, the sensor is actually overestimating the true mass concentration as measured by the PDR instrument. And so here's just another way of looking at that for an outdoor study in Chile. Generally good correlation between the Plantower and the BAM that they're using this as their reference. Decently good agreement with PM2.5, but there are some cases where the sensor is either under or overestimating the mass concentration. This is more pronounced for PM10 here on the right-hand side. There are these periods where the sensor is overestimating the true concentration. There are these other periods where it's underestimating the true concentration. And so these issues are related to the fact that most of these sensors are like nephelometers. And so what this means is our particles enter our device, they pass through this channel until they reach this point where they interact with the light source. Upon interacting with the light, they scatter it, and that's what we're actually detecting in nephelometers. That's how most of these sensors are actually functioning. They're detecting that scattered light signal. And so if we're thinking about the nephelometer measurement in outdoor air, we call this quantity that's being output a scattering coefficient. And so what this scattering coefficient really is this integral over a range of particle sizes that we can think about as the product of our particle size distribution and the scattering cross-section for each particle size. So we have this product, we're integrating over all the particle sizes, getting a single output value from that measurement. And so in outdoor air, we can do things like relate the scattering coefficient to a mass concentration of particles by assuming something like a mass scattering efficiency. But again, that's giving us a single mass concentration output. And so what this means for these sensors is that most of them are calculating, not measuring PM1, PM2.5, and PM10. They're doing this calculation most likely by assuming some underlying size distribution. And so this figure taken from Jess Schreiner and a group at Colorado State, they basically challenged the Plantower sensor with different size PSL spheres. So 0.1, 0.27, 0.72, and 2 micron spheres. And their reference measurement are in the solid bars. And so we generally see this change in the measured size distributions as we're increasing those particle sizes. But what's happening in the sensor itself is we have this fairly consistent response in these lines, in these figures. And there's this consistent underlying distribution of particle sizes in what the sensor is outputting. So it seems like they're assuming this underlying size distribution that enables them to do this apportionment of sizes. And so yeah, this is something consistent was shown in prior work by Meilu He and a group at Clarkson University. And so along the lines of size, there's also potentially losses due to particle motion. And so thinking about things like aspiration efficiency, which is actually getting the particles into the sensor, and transmission efficiency, getting the particles through the sensor. And so using this schematic taken from this Siahi et al. Paper, we get the particles into the sensor. This is the aspiration. The particles pass through the lower level, come up through these air holes into the upper level before they reach this detection region with our light source. And so transmission is all this path through the sensor until we reach this detection point. And so it's maybe less obvious from this figure, but there are these two 90-degree turns that the sensors need to make as they go from this lower level up to this upper level. To do this, we need to know something about the flow through the sensors. And Wimet estimated this is about 0.1 liters per minute through Plantower sensors. And so using that and using some empirical relationships for aspiration and transmission efficiency, I came up with these curves just to demonstrate what this looks like. And so this aspiration efficiency function from Durham and Lundgren is a function of the angle of misalignment theta, which is I'm really considering this as misalignment because if our particles are traveling horizontal in the air, they need to make this 90-degree turn to get up into the purple air sensors if we're deploying them like most people typically do. And it's also a function of the Stokes number, which is a function of particle size in addition to some other factors. And so generally, based on this calculation, we're losing particles mainly above 10 microns. Similar for transmission efficiency, again, taking this relationship from Pui et al. For 90-degree turns, we're getting similar but fewer losses due to aspiration because of those 90-degree turns. And what this is ignoring is it's just assuming those turns. I haven't accounted for any other internal losses that may occur through things that aren't turns in the system. But generally just losing particles greater than 10 microns for this 0.1 liter per minute flow rate through the sensors. And so that's sort of size effects, but composition can also play a role. So going back to another figure from Long's paper, looking at the response of, again, that Shinye PPD sensor to sodium chloride particles, sucrose particles, and ammonium nitrate particles, we again see these different responses based on these different particle types. So for sodium chloride, we have this fairly linear response over this entire range of particle concentrations that are measured. But for both the sucrose and ammonium nitrate, we see these asymptotes that above certain concentrations, we're not really seeing much of an increase in the response from the sensor. And so one of the ways that the composition can affect the sensor's accuracy is through their complex refractive index. And so on the left-hand side, I'm plotting curves of scattering cross-section taken from the model that Hagen and Kroll put forth in their atmospheric measurement technique study for non-absorbing aerosols. And so for these non-absorbing aerosols, they all have generally the same response in the predicted scattering behavior using me theory. But if we think about absorbing aerosols, so I just have a representation of black carbon and brown carbon here, we start to see very different responses. So for black carbon, there's about half an order of magnitude greater in scattering response below around 300 nanometers or so. And above 300 nanometers, there's less of a scattering response compared to the non-absorbing aerosol. And for brown carbon, it's kind of a similar response up to about a micron, and then we have this divergence. So if we think about composition effects and the complex refractive indices, it makes sense that these are light scattering technologies, so the responses should be different if the light scattering response of the particles is different. But the sensor hardware can also play a role in how the sensor detects these particles. And so here's just two figures taken from again that Lumet study, where they're comparing an ideal nephelometer, the normalized power for an ideal nephelometer, to two representations of a Plantower sensor. And there's relatively less normalized power for these two representations above around 300 nanometers. And then this is just looking at how the detector is actually positioned and how that can affect the relative response as a function of scattering angle. And so basically what the sensors can detect is limited by both aerosol motion and sensor optics. And so finally, moving on to some of the work that's actually in the paper. In phase 1 of our experiments, we're looking at the effect of particle size. And so here we generated two types of particles. We modified a propane torch so it burned less efficiently and produced a lot of soot. And we also atomized some ammonium sulfate solution. For both of these sources, we then passed those particles through a DMA so we could select a given size. We introduced the size selected particles into a chamber containing our sensors. And we measured the number concentration in that chamber using a CPC. And we converted those CPC number concentrations to mass concentrations using the selected particle size and assuming densities on both of our sources, so we could compare a measured mass concentration from the CPC to those estimates of mass concentrations from the sensors. And so in our data analysis, we mostly used linear regressions because our data generally followed these trends that could be described by this y equals mx plus b relationship, where x here is our reference data, y is our sensor data. And we also consider the coefficient of determination, or r squared, from these regressions. And so we're using the slope and intercept as metrics related to accuracy. So as the slope goes to 1, as the intercept goes to 0, we have a highly accurate sensor. And as precision goes to 1, we have a highly precise sensor. Whereas r squared goes to 1, we have a highly precise sensor. And so here's some of those results for a Plantower sensor that we tested. Y-axis in both panels are the diameter of the particles that we size selected. In the top row, we're looking at the slope. In the bottom panel, we're looking at the r squared. And the blue represents the propane torch results. The orangish red represents the ammonium sulfate results. And so what we're generally seeing is this increase in both the slope and r squared as we're increasing in particle size. So it appears that as we're getting larger size particles, we're becoming more accurate, we're becoming more precise. And so these results are similar to some previous work. And so this is taken from Kula et al. from AMT 2020, where they were using a VOAG, so looking at these larger particles generated from that. This region that I've highlighted with the circle is sort of we have this overlap in our results. And for particles in the 5 to 700 nanometer range, they're seeing about 50 to 70% detection efficiency, which agrees relatively well with our slopes ranging from about 0.5 to 0.75. So in phase 2 of our experiments, that's really where we started to look at the role of composition. And so the exact procedures varied slightly between these different sources, but generally we had compressed air that was HEPA and carbon filtered. We're generating again the atomized ammonium sulfate particles and the propane torch. We also added some incense and some toast smoke, and as well as some Arizona test dust to this mix of particles that we were looking at. Pass them through a dryer into a chamber containing the sensors, and then again we're using SMPS plus APS as our reference measurement, so we can get these time series of the particle size distributions, even though the SMPS and APS aren't exact measures of particle mass concentrations. And so generally, our accuracy is variable, but the precision is good. And so that's what we're seeing here on this figure. Again, we have slope in the top, R squared in the bottom. But this is the total mass concentration of the PM10 output by the sensors. The most, or the slope closest to 1 was for incense in this case, slope around 0.8. Lowest slope was for the Arizona test dust, slope around 0.45 or so. But generally very precise. With R squared, it's greater than about 0.75. But of course, we're looking at composition here, but we can't totally deconvolve that from size. And so what I have in the middle here are some mass median diameters for these experiments. So for the torch, the mass median diameter is around 0.3 microns, 0.5. I won't read all these, but I will highlight that we did have these bimodal distributions for both incense and toast. And then this result for dust with the largest particle size maybe doesn't surprise me, given some of the previous results, like the one we looked at from Kula. But these variable responses to different composition particles, again, are consistent with other work. So another figure taken from Jess Triner's paper. Here we're just going to look at the orange circles, which is the Plantower in this case, for both ammonium sulfate and Arizona road dust. All these figures fall below the 1-to-1 line, and so that's consistent with our results that we were sort of underestimating the actual mass concentration of these two particle types. For urban PM, there's sort of this exact match here, and my understanding is that the Plantower sensors are calibrated using air in Beijing. So it makes sense that urban air is sort of has this good agreement because that's how the sensors are calibrated. And then here, for wood smoke, it's sort of overestimating those mass concentrations, which is consistent with some other field work. So one other sort of quick sidestep to explain some more data analysis. So now we're going to look at size fractions. So we're using the sensor calculated PM1, PM2.5, and PM10 to split these into different size fractions. So looking at just PM less than 1, PM from 1 to 2.5, and PM 2.5 to 10. And I have this cartoon here at the bottom of the figure to show how we treated our reference size distribution. So basically we integrated the area under the curve for everything less than 1 to be a proxy for this PM1, between 1 and 2.5 for PM1 to 2.5, and between 2.5 to 10 for this other size fraction. And so the accuracy of this apportionment into the size fractions is again variable. And so knowing what we know, that these aren't actually measured and they're sort of calculated, this makes sense, right? The sensors aren't actually measuring these size fractions, they're just calculating them based on some assumptions. And so with the exception of the propane torch, we kind of have the lowest response in either the PM1 or the PM 2.5 to 10, and this PM1 to 2.5 is kind of always the highest. And again, just those mass median diameters as points of reference. And again, looking at this figure from Misty Levi-Zamora again, our sort of variable apportionment is consistent with what others showed. That sometimes we're over apportioning, sometimes we're under apportioning. But the question is really, how can we account for all this for these indoor applications that we're interested in? So for outdoor air, calibrations exist. And so I'm just showing an example of one of those from a group at US EPA, where they have basically a multivariate linear regression that's accounting for, it's correcting the purple air concentrations for PM 2.5. And so it's accounting for both the raw value output by the sensor, it's accounting for the relative humidity in the ambient air. And so after applying this calibration, there's generally this good agreement between the corrected purple air PM 2.5 concentrations and FEM or FRM measurements. But for outdoor air, this sort of calibration makes a lot more sense, I'd argue. And so this figure on the right's a figure taken from another asteroid project led by Brandon Bohr and his PhD student, Tianren Wu, that globally these urban size distributions are roughly consistent. And so I forget the total number of studies that they actually compiled here, but this dark black line is sort of the median across all these studies. Again, generally consistent. The issue with thinking about outdoor calibrations for indoor air is that we have a lot more heterogeneity in different rooms within buildings, because we don't have that mixing like occurs in outdoor necessarily. And so here's just some representations of different size distributions of different sources of particles. So we have something like a natural gas burner, which has a mass median diameter of around, or a number median diameter of around 30 nanometers. Candles around 50. In yellow, here's a meat cooking, which is between 1 and 200 nanometers. Here's our incense representation in the green with the bimodal distribution, and an approximation for resuspended house dust, which has this median diameter of around 2.5 microns. And so we have this variability in the size because we have this heterogeneity in sources that may exist within different rooms within a building. And so it may be more difficult to apply those calibrations. I'll skip this. Another issue is that in some cases there may be large unit-to-unit variability in these sensors. And so here's just some work from Zakova et al., where the black line is the reference, and these gray lines are the different sensor units. So there's about a 10 microgram per cubic meter difference between the maximum and minimum concentrations in those lighter gray curves. And so that last slide I inserted before this slide by accident, so apologies. Getting back to calibrations, size-specific calibrations exist, but we need to know that size a priori. And so this is work from Lee and Biswas, where they have sort of these size-specific calibration factors. But if we're thinking about one of these low-cost sensors, we're just getting that single output from those sensors. You don't actually know the size of the particles to apply the calibration factors, unless we also have something like the AlphaSense low-cost OPC. And so kind of the question that I'll pose, I don't know if I have an answer to this, is can we connect something with indoor air quality to light scattering? And so in that paper from Lamette, they were looking at answering the question, could we use a purple air sensor as a light scattering device? And so generally the takeaway is that above about 1 inverse megameter or so scattering, there's this pretty good response in the channel 1 average. And so that's the lowest, or the output of, that's the output for one of the number bins that the sensor's outputting. And so potentially this is a much more less error prone metric we could use that's not accounting for differences in particle size. We don't need to worry about converting to mass concentrations, but operationally, I don't know how we do this. So really to summarize, the size effects appear to be a larger driver of variability through some combination of actually sampling the particles and or their scattering behavior within the sensors themselves. The sensors appear to be okay for outdoor applications. There are some calibrations that exist, but for indoor applications, most low-cost products may be prone to inaccuracies. And really the question, and I definitely don't have an answer to this, is what is good enough? I think that's sort of up for the user to decide, and as long as they know that inaccuracies may exist, is that okay for the application? So with that, I'll open the floor to questions.
Thank you, Dr. Andy May. We have a lot of questions. So the first question is, are they assuming sizes or just better at detecting smaller sized particles?
Is that question relating back to?
Yes, I believe it's about Plantower sensors.
So oh my goodness. Yeah, I'm
actually, you could unmute yourself as well, just to clarify.
Yeah, so I'm assuming that that's referring to this slide, and it really seems like the sensor itself is really just assuming this underlying size distribution. I don't think it's really saying anything about detection efficiencies.
Okay, next question is, are slide 22 graphs at 90 degrees scattering or overall scattering?
This is, what I've done here is integrating over, I think it's 70 to 173 angle. So it's integrated over a range of angles. So it's not just a single angle. I'm pretty sure that's what David wrote into the model, and I didn't really tweak that much.
The next question is, are these models, as in for R squared, as in y equals to mx plus b, or mean square error based R squared, like fit around 1 into 1 line?
So these are, let's see. These are the coefficient of determination for this linear model. So we're just using ordinary least squares because we're assuming that we have much less uncertainty in our X data than we do in the Y data, as opposed to doing something like reduced major axis regression, which is minimizing a different distance in that regression. We did do some of that for other work as part of this project, but not what I'm showing here today.
Okay. Is it the size distribution of the Arizona test dust that make it to lower slope and R-square values? Slide 30, maybe.
So possibly, I think sort of our underlying hypothesis for why this is much lower than the others is because they are larger particles. Again, we're resuspending some of these dusts, which I forget if I actually said that or not, but we're resuspending the test dust. It had this mass median diameter of around 2 microns. So it tended to be larger, and I'm assuming that perhaps this more so than the others was affected by some of those sampling issues through the sensors.
Okay. The next question. I see you choose mainly linearity slopes and R-square for your matrices. Did you look at mean absolute errors for your evaluations?
I don't recall if we did or not. If we did, it wasn't one of the. I mean, we're using these slopes in R squared as sort of the main metrics in our analyses, but I don't remember if we used mean absolute error or not. So I can't really answer that question. Sorry. I don't think we did.
The next question. Are the purple air sensors calibrated to the EPA standards? Like, are these slides 31, 32 purple air?
So in our results, we didn't apply any additional calibrations to the sensors. We're just kind of taking them effectively out of the box and using the as is reported values. So I guess the short answer is no, they're not calibrated, because we're interested in, like, assuming we're some like agnostic user, how would these sensors be responding in our experiments?
Okay, next question is a bit long. So most optical reference apparatus are also using calculations to assume mass per volume concentrations. Can you comment on the impact on the displayed results and corresponding interpretations on accuracy and precision in these cases?
So I'm less familiar with optical references, and without specifically knowing what that question's referring to, I don't really know how to answer that one, unfortunately.
Daniel, could you unmute yourself and maybe give more explanation?
Yes, I mean, for example, the GRIM apparatus is often used as a reference sensor, and it is also using calculation to assume what is, or infer what is the actual aerodynamic diameter from its physical diameters. So they are translating in some ways the correspondence between, and they are also assuming some density from these particles. So that could also suffer from calibration issues when you change the composition of the particulates.
Yeah, so like I said, we didn't use anything like that, but yeah, that's perfectly valid point that with a lot of these things we're making assumptions. And so like with our SNPS and APS measurements, we assumed densities of the particles based on literature values. And so, I think some of that question is best answered with what's the accuracy of those assumptions. I don't know. I think accuracy may be the main impact there. I think precision may be less impacted by those assumptions because that's more looking at how is one responding relative to another, regardless of the magnitude of that response.
Okay, next question. Did you do any unit-to-unit calibrations of the sensors before testing?
So we didn't do any unit-to-unit calibrations. We did do a unit-to-unit comparison, sort of this pairwise comparison of the different sensor types. So we had like 3 purple airs that we were using. We had 3 bare Plantower sensors. We had a suite of others. And as part of that, we looked at how they compared among the replicates. And so I think generally I'm trying to remember results from a different paper. This is in that Science and Technology for the Built Environment paper that, I don't know, I see Jeff Siegel has a question. He's probably one of the few people as an ASHRAE member that actually has access to that. But we have it in there and I can share that if people are interested.
Next question is, can you please comment on the use of these Plantower sensors for relative measurements, example decay rates, versus absolute measurements for indoor applications?
Yeah, so I think if we come back to this figure, where we're looking at those sensor responses, generally the sensors are returning back to the baseline around the time when the reference instruments are. So yes, I think if we're thinking about something like decay rate and knowing Jeff a little bit, I'm assuming this is somehow related to ventilation. From that sense, yes, maybe these do have that utility. Whether or not that absolute magnitude of the response is accurate or not. If we're kind of looking at, is it returning to baseline, then yeah, we maybe the actual accuracy in that baseline doesn't matter.
Next question. For indoor low-cost sensors, do calibration factors have a measurable impact if the inaccuracy is deemed to be consistent across multiple calibrations?
I guess I don't quite follow that question. Is it possible to unmute and clarify?
Would you want Sohaib to unmute himself?
Yes, that's what I was hoping for clarification.
Sohaib, could you unmute and maybe explain more?
Yeah, sorry, I just had to move to someplace quieter. So let's say if in the case of like calibrating low-cost sensors to more expensive sensors that are research-grade equipment, if you find that the slope is usually within a certain range, like when compared to the research-grade equipment such as GRIM or APS, can you apply like a calibration factor looking at the slope or the R-squared value? And do you think that would have like a good impact on, making the precision and accuracy of these sensors like better?
So you're basically suggesting, like, if we have something like this, where we have a fairly linear response, the R squareds are likely high here. I don't know what they actually are, but we know there's linear regression, so we could use that as a calibration equation. Is that
Yes.
what you're
Yeah.
suggesting?
Yeah.
Yeah. So I think, and this is maybe something that it should have been explicit in saying. We think that if you have a more precise sensor, it's more likely that you can come up with those calibration equations and have those calibrations be more reliable as you apply them, because you're not dealing with that imprecision that could affect those calibrations. I think the issue for indoor air especially is that maybe you'd want to do your calibrations where you're going to be using them, which is potentially a huge barrier, especially if these are, for personal use in somebody's home. Are they going to like rent equipment to do a calibration? I don't know. That's kind of some of the underlying challenge, I think, with personal use indoors. Does that answer your question?
Yeah, perfectly. Yeah, thank you. Appreciate it.
Next question. Where does the vent of the sensors go during the testing in the chamber?
Stays in the chamber. We didn't do anything to vent what was being sampled by the sensors out of the chamber. So conceivably, anything that wasn't lost was just recirculated. But we didn't see appreciable changes in particle size distributions in the chamber. So it's not there's nothing that suggests that we were sort of biasing our results by somehow causing the size distribution to evolve throughout the sampling.
Okay, another question is, does the accuracy of low-cost sensors changes with the PM concentration?
So the short answer is yes. And in some of our, I think in our indoor air paper, which I forget if I referenced at all here or not, we're actually looking at like what are the bounds of quantification for these sensors. So what's the lowest reliable concentration that they can measure? What's the maximum concentration that they can measure? And so below a certain threshold, they just kind of seem like they're spitting out noise. Above a certain concentration, we see something similar to Yang's work, where we have these sort of plateaus above which the sensors no longer respond. But in between there is that general linear region that seems to be fairly consistent. I think that answers the question.
Okay, next question. You imply that these sensors are more reliable in outdoor applications. Does that cover different aerosol types? Example, rural versus urban versus maritime?
Yeah, so I guess in my statement, I was thinking more about airborne applications. That obviously when we move to rural or marine locations, we are going to have very different aerosol populations. So potentially reliable with an asterisk under, if we're only using them in certain locations where we know these are pretty well characterized. But I think if we're going to deploy these in rural or maritime locations, maybe we're going to think about different calibration equations just to make them more accurate in those cases.
Next is just a statement or a comment. Remy Losno says that thank you for the clear presentation, and your final statement that what is good enough is the key word. Okay.
I'm glad somebody else appreciated that.
I would move to the next question. During an urban campaigning, I saw that PM10 by PM 2.5 ratio is almost constant over days. It has no sense. What do you think?
I mean, without knowing more details, I think that I'd agree with that. But like if it's using something like a purple air where it has that assumed underlying distribution, then yeah, it makes perfect sense because it doesn't know what the actual size of the particles are. So it's just sort of doing the calculation to spit out those results.
There is a lot of chat going on, but I would ask another question. So it says, for your experiment, did you assume all particle sizes were spherical? If not, how did you arrive at the sphericity aerodynamic sizes of the particles?
So I think we assumed that everything was spherical. For most of our particle sources, we could find some reference of the actual shape. I think the only exception may have been the ammonium sulfate particles where we assumed, I forget what that shape factor is, but I think that was the only exception to the spherical assumption.
Okay, there's next question. Fitting of these low-cost sensors for ambient PM monitoring seems important. I'd seen them mounted on large house walls. Doesn't fetch play a role, and did you examine such effects?
So I'm assuming that that's something about like what's the airflow around the sensor, Carsten, is that correct?
Yes, exactly. I mean, apparently, if you put a sensor in a shaded area, protected area where free airflow is inhibited, and you're subject to maybe a boundary layer of the object forming around that object, then you can be as accurate as possible with your optical analysis. The particles get separated due to the micrometeorological effects. So did you make any tests for that?
Yeah, so that's not something that we were really focusing on as part of this work, but yeah, I agree that that is a potential concern with these measurements, that how the air is actually flowing towards the sensors themselves is another sort of, I guess, efficiency in terms of actual sampling.
Thank you.
Okay, we do not have any more questions in the chat, but if you have more questions, please feel free to unmute yourself and ask the question. We can have another 1 or 2 minutes. So if you have questions, just let us know.
Well, Andy, you mentioned that the purple air and other nephelometers are systematically over-predicting the wood smoke particles. What do you attribute that to?
I've thought about that, and I have no idea.
Okay, fair enough.
but I'll be honest. Like I say, I've thought about it, but I haven't really thought about it. If that makes any sense. Like there's perhaps some mechanistic reason, but I don't have an answer.
Something to investigate, I guess.
Yeah.
All right, we are right on time. Dr. Andy, everybody's thanking you for the work. Thank you so much for presenting a great talk. With this, we can end this session. Thank you all.
Thank you.
Well, thanks. It was a great job to everyone. And we had almost 160 people. So awesome. And a very lively discussion. So that's even better.
Yeah, I rushed through some things when Shruti said 15 to 20 minutes for questions. I was like, oh.
Yeah, no, it was totally perfect. It was perfectly timed.
I'll try and finish a little early so we can have more questions.
And we had lots of questions, and definitely I think lots of people will be excited to see the recording too. You know.
So is it okay if I drop out? Because
yep, so we can go ahead and end the meeting. So thank you, everyone.
Right, thank you.
Thank you so much. Thanks, Dr. Andy.
I have a 2 o'clock meeting. That's why I'm asking.
No, you're totally good.
Thanks.